Today we are going to discuss on quantifying hydrogen injection limits. So in this presentation on hydrogen injection in blast furnace, which is a journey towards decarbonized iron making, which asks us a question that how much hydrogen can we inject into blast furnace while staying within thermal and permeability constraints. In this talk, we'll explore a validated modeling approach that quantify these operational limits and reveals the real CO2 reduction potential of hydrogen. So now coming to the model overview. This work uses a two-stage heat and mass balance model, and it is calibrated to a real operating blast furnace. So let me explain its structure of the model. The lower stage below 1000 degrees Celsius covers coke gasification and solid state reduction reactions. The upper stage above 1000 degree captures melting, slag formation and energy redistribution. So all this major activity, and between these stages lies the chemical reserve zone centered around 850 degrees centigrade, where iron oxide react with gases near equilibrium. So, to simulate incomplete reduction, the model uses a parameter called a stack reduction efficiency, or SRE, which quantify how much FeO escapes reduction. Now, let us discuss the base case condition and constraint. The base case parameters reflect typical large blast furnace conditions. So, here we can see hot blast temperature is 1153 degrees centigrade, moisture content is around 10 grams per normal meter cube. Similarly, hot metal temperature 1522 degrees centigrade with 5% carbon. Slag temperature 1572 with a basicity of around 1.2. And the to prevent the operational issues, the model imposes two key constraints. What are those two key constraints? And all operators also know these are about a minimum top gas temperature, which is here 118 degrees centigrade to avoid any AC dew point corrosion, and a minimum draft of 2050 degrees centigrade, which is 200 degrees centigrade below the base value. Now let us see the case definitions. Four operating cases are modeled to evaluate hydrogen's impact under different conditions. So let us see case 1. Case 1 is about fixed hot metal production with PCI as the variable fuel and SRE at 0.91. Similarly, case 2, fixed boss gas flow rate still with PCI and SRI at 0.91. Case 3, fixed hot metal rate but with coke as the carbon source instead of PCI. And case 4, fixed production and PCI but with an ideal SRE of 1.0, representing perfect reduction. So, each case helps isolate the impact of hydrogen on draft, top gas, coke rate, and emissions. So, now coming to the operating parameters at maximum hydrogen injection. Here are the operational parameters when hydrogen is pushed to its allowable limit. In case 1, we achieve 19.5 kg of hydrogen per ton of hot metal while holding the coke rate at 364 kg. PCI is reduced to 102 kg and dropped to minimum 2051 degrees centigrade. In case 3, using coke instead of PCI, the coke rate can drop further to 333 kg per ton hot metal, 333 kg per ton hot metal. Coming to case 4, it shows how improving a stack reduction efficiency allow a much greater fuel replacement ratio even though the allowable hydrogen injection dropped to 14.3. Now it's a time to discuss on key results. So we can say the main outcomes. Under a typical SRE of 0.91, hydrogen injection reaches 19.5 kg per ton hot metal, displacing 37 kg of PCI and reducing CO2 emission by 8%. With SRE improved to 1.0, the hydrogen cap lowers to 14.3 kg per ton hot metal, but it replaces over 4.5 kg of PCI per kg of hydrogen, leading to 14% CO2 saving. However, this comes at a thermal cost. Hydrogen lowers the raceway flame temperature and top gas temperature, so maintaining operational stability demand oxygen enrichment or higher blast volume. So now let us see, let us explore the physics behind these constraints. So when hydrogen burns, it forms water vapor which absorbs latent heat and cools the raceway. Coke, by contrast, not only fuel the furnace, it also maintain permeability and gas flow structure in the body. In case 3, the coke rate is reduced to 333 kg per ton hot metal, and that's likely the minimum permissible level without jeopardizing the cohesive zone stability. That means even if hydrogen is clean and reactive, there is a hard floor for coke dictated by the mechanics and thermodynamics of the furnace. So finally, reaching to the conclusion, or we can say to wrap up to 20 kg of hydrogen per ton of hot metal can be injected under current design and safety constraint. So this limit is 20 kg. At constant SRE, you gain an 8% cut in CO2 with improved reduction efficiency, saving rise to 14%. Further benefit demands pilot trial to validate model predictions and optimize oxygen enrichment and injection strategy.